So as we continue our study of simple harmonic motion, here we will investigate the horizontal oscillations of a mass spring space system. So let us first try to understand and imagine what a mass spring system is. So let us say we have a rigid support, and let us say this is a frictionless surface or a frictionless table, and to this rigid support is attached a spring. Let's say this is a spring and this is attached to a mass. So this is what we mean by a spring mass system. So you have a mass attached to a spring and lying, let us say, on a horizontal surface like this. Let us say the spring constant of the spring is equal to K, and the mass of this block is M. And this is the equilibrium position. That means the mass or the spring, neither of them are moving back or forth. So I'll indicate this as the equilibrium position of the mass spring system. If I want this to oscillate, I'll have to pull this mass in this direction or compress this mass in this direction. Let us say we pull this mass in this direction. So we will have a situation something like this. Let us say we have this, I draw the second state of this, and so the mass will now say move over here, and the spring will elongate. So you will have a situation something like this, and the spring has elongated, and let us say we are holding the mass over here, not allowing it to move back and forth, and let us say this displacement is x. So I have displaced this mass by a distance x, and let us say now I release this mass. What we will immediately see is the mass will start going back, right? And that would mean that when I am holding this mass over here in this position, there is a force which gets generated in this spring, which has a tendency to bring this mass back to the equilibrium position, back in this direction. And therefore I denote this force by F, and this force is known as you would have studied earlier, the restoring force. The restoring force tries to get back the spring into the equilibrium position. And by Hooke's law, we know that F is equal to minus Kx, where K is the spring constant of the spring. And the minus sign because the force is acting in this direction and the displacement is in this direction from the equilibrium position. So F is equal to minus Kx. We could have taken the case of also of compression, and we could arrive at the same equations as we will be doing now, but I have taken the case of expansion of the elongation of the spring. Right, so we have this spring, we have pulled this mass over here, and when we release this spring, what will happen is this mass will go in this direction and it will overshoot this position. The mass will go further down and then start, and when it goes over here, the spring will get compressed. Therefore a restoring force will get generated in the spring in the opposite direction. That means it will get generated in this direction and it will start going back, and what we will observe is this mass oscillating back and forth around this main position. This is what would happen if I release the spring. Now, when I release this mass, let us say when I release this mass, at that instant, the acceleration of this mass is, let us say, alpha. Now, alpha is equal to force upon mass. Right? The force which is applied on this mass is the restoring force F. M is the mass of this particular block. So, alpha is equal to F upon M. I repeat, alpha is the acceleration of this block the moment I release this block at that particular moment. So, alpha is equal to F upon M. And therefore I can write F is minus Kx upon M. So I can write this equation as alpha is equal to minus K upon M into X. For a given spring system, K upon M is constant because K is the spring constant, so that is going to remain constant for this spring. M, mass of the block, is going to remain constant for a given mass spring system. Therefore this is constant, and therefore I can write down alpha is proportional to minus X. And this, you know, is the condition for SHM. And therefore we say that when this mass starts oscillating around the mean position, it is performing simple harmonic motion. Alpha is equal to minus Kx. Okay. We also have studied that T is equal to 2 pi displacement upon acceleration. This is the standard equation for time period of simple harmonic motion. So what will we get in this case? Is equal to 2 pi upon displacement upon acceleration. So displacement is x, acceleration is alpha. So that will give me 2 pi upon. Now if I use this equation, what do I get as x upon alpha? I'll write it over here. X upon alpha would be equal to x upon alpha. I take alpha over here. That would be equal to minus m upon k. So for x upon alpha I can write down m upon k. I'm sure you have guessed why we are ignoring the minus sign, because time period is a scalar quantity. This minus sign only indicates the opposite direction of the displacement and the force. So therefore I am ignoring the minus sign. I get this equation t is equal to 2 pi m upon k. So what does this equation tell us? It says that the time period of a mass spring system is directly proportional to the square root of mass. That means it is directly proportional to, so if this is a heavier mass, the time period will be more. Similarly, it is inversely proportional to k. That means if higher is the spring constant, that means stiffer the string, you'll have, that means in that case time period will be more, because a stiffer string would require this. So this also shows us a relationship between stiffness of the spring and time period of the spring mass system. If we look at the real life application, for example, if you want to understand some of the real life examples of a spring mass system, we have that in case of a car. For example, a car has what are known as is. In case of car, we have this shock absorbers, and basically they play the role of absorbing the shocks, and if they're not working well, we have an unpleasant journey, because the shocks get transferred to our body and we're not feeling comfortable with that. And just for the sake of exercise, what you can do is you may want to calculate the, say for example, the restoring force acting on a car. For example, if I take, let us say, the mass of a car as say 950 kilogram, and let us say the spring constant of the spring used is let us say 6.5 into 10 raised to 4 Newton per meter, and you can calculate the force acting over here, the force that is acting on the spring. So this will give us you an idea about what is the restoring force acting on the spring. Okay, in the next video we will investigate the horizontal oscillations of a mass spring further, and what we will try to look at is what would happen if we have a system like this. For example, you have again a horizontal surface, frictionless nearly, and we have a spring, and we have another spring, and then we have a mass attached to it. And these two have, say for example, different values of spring constant. In this case, what would be the time period and how the system or these calculations would change? That is up for discussion in the next video. Thank you.